Okay, I am glad to present Heiko Braun, who will tell us about theta n trees and disks. Heiko, please take it away.
Thanks for the introduction. Yeah, let's see what theta n is. Theta n is the specific subcategory of n categories. And I think the best way is to start with pictures. Oh, sorry, my pen sometimes makes pictures. Okay, how does it look? So the objects, so the n categories that are in there, let's maybe call them theta. They look like this, for example. So this, this is an example for n equals 1. It's just that theta 1 by definition is delta, which is in ordinary categories. So delta of the simplex category lives as a full subcategory of cat. And then what we do in the higher cases is always, for example, n2, a generic example there would be maybe this. And the thing what we do is, in general, theta n are linear categories enriched over, and then this is repeated, enriched over linear categories. And here this times is n times. Therefore, we have maybe a slightly more dimensional picture that it looks like we have something, then we have morphisms there, and whatever we do, in the end, it's always a string of these morphisms, and at the end, there will only be one. So, for example, the end part is here. This is now, let's count it. It's a 1, 1, 2, 3, 4 category. So this is in theta 4. And you can see that when we just dissect it into these parts, so here, and then we have just each part is like linear. We have this object, this object, this object in the first level, and on each of the parts, when we turn our heads by 90 degrees, it again looks linear, and it's repeating like that always. Okay, and this is already the the full definition, and now we just say that theta n is the full subcategory of n categories on these linear categories. Maybe I put this here. On these ones. Okay, but this seems maybe not too difficult, but still one has many other equivalent ways to write this and to state this and how to work with them. The pictures here are, with time, it becomes a bit cumbersome to draw them. So we use another method to draw them, and this is what are trees. So how do trees work? Let me just again draw some pictures of example theta n categories, and then the corresponding tree of that. So what is possible? Maybe start with this one here. In the case n equals 1. Then we have, okay, here points. In the corresponding tree, we think we write it like the following. We have a root, and 2 edges that go up. Maybe I don't draw the arrows on the tree. Okay, and the thing is, how this corresponds to each other is that we have these 3 more objects, and they correspond to the 3 sectors of the trees. And the morphisms, they correspond to the edges. And then in the next step, on 1 dimension up, we could maybe do the same thing, but then turn it into a higher category. Now let's go to the next dimension and just copy it and add some stuff. For example, we could add another morphism here. In the picture, okay, we must, if we add a morphism, then we also must add an edge. This would maybe be that. And now in the picture, this would correspond to adding a line here to a next dimension. And the 2 vertices, the 2 morphisms there correspond to the 2 sectors here, and the morphism now to the edge. So that's how these things work out with this corresponding to the trees. Maybe another basic example, which is very important, is the most, maybe the easiest trees are the straight line trees, so linear trees. They look like this. And you can see that there's always 2 sectors in each dimension, but in the last there is more or less only 1. And so what does it correspond to? This corresponds to the category that has 2 objects, 2 morphisms in the first dimension, then 2 morphisms in the next dimension, and then we are done because it's only for a 3 category. So this one here. And these things are known as cells. I call this E4, E3. Just for convenience, E2 would just look like this. And E1 would be this one. And the corresponding trees are just the same, just chopped off at these places. Okay, but why are we interested in this theta category at all? So we have now seen how to draw this, at least to give the same information, maybe a bit less cumbersome way, because it is possible now to really nicely embed it in the plane as these trees, instead of drawing longer and longer curving arrows, which may be difficult. But apart from this, what is the reason why we consider these? So an important part why it's interesting is that theta n is actually a dense subcategory. Theta n in nCat is a dense subcategory. And this means that by definition, this denseness, it says that when we consider the nerve which goes from n categories to tree sheaves, so functors from theta n up to z, that takes an n category C to the functor that takes some theta to the n category morphisms of theta to C. This is fully faithful.
Sorry.
Yes?
What is the definition of the n categories you use here?
Ah, yes, sorry, I forgot to say this. These are strict n categories. So let me write it. N categories are strict n categories. So in the sense, define 0 cat as just sets, and n+1 categories are defined as categories enriched over n categories. Maybe like this. So enriched over n categories, it's strict. It then comes down to strict n categories. So there are, in the sense that when you look at these pictures, then you have these morphisms, and of course I only drew the graph of the category. But when you have such a thing here, so for example, this morphism and this one, then you can of course compose them together. And moreover, you can also do higher compositions. For example, when you have the cell, you can obtain from there a composite cell between these compositions. For example, so if we can compose the bottom arrows and this one, this arrow, then there's also a cell in there which exists. And in this sense, there are like the higher morphisms as well, and it's all strict. Okay. Now.
So what about coherence conditions?
Yes, there are coherence conditions. These are just there's things like the interchange law, home must hold in n categories. For example, when you have this situation, then there are different ways how to compose these four morphisms, these 4 two-morphisms. There are 4 drawn two-morphisms now, 4 two-morphisms. And this is now also the reason why I draw them from right to left and from down to up, because if we give them names, then let's call them maybe A, B, C, D, then A, B composed with, well, I don't know, composed with, maybe I should draw this here. AB composed with CD is the same as AC composed with BD, for example. And you see already there are different ways to compose relations, morphisms. In this case, this notation means that we compose vertically to a complete morphism from here to there. And the other relation, the other symbol means that we compose horizontal in this direction. Yeah, but
yes, but this is not a strict definition.
Well,
we have some examples, but we have no definition.
Yes, this definition, of course, one can give a definition here. So when we have we need to define what is enriched category. Then I can do that now. Maybe just put this here. So if we have so if we have any category, V should be monoidal category. Then we can consider enriched category over that. And enriched can consider enriching a category over this and enriching over V. And what it means is when we have, for example, an enriched category over V is then a collection of objects. Let's write it, I don't know, C0, or no, object C0, object C maybe. This is just a set. And for all possible, for all compositions, and for all pairs X, Y in these objects, we have an object of V. So C of X, Y, but this is crucial, lives in V. And now we also need to add compositions, namely plus, as well as composition and unit morphisms. That is, we have and we have this iteration cy was cy comma z, not this. Sorry, we use the monoidal structure of our category V. So there's some notion of tensor product on this. This is just notion of tensor product, or in our case, the monoidal structure will be the product. So I just write notion of product of objects to make a third object. And then there should be these morphisms that compose goes to Z. And as well, this was the composition, and the unit part is always an identity object in V. And there should be a morphism that goes to CXX. And this is true for all X, Y, Z. Yeah, and then such that specific relations hold. So there are relations that say that the composition is associative and the unit is really unital. And yeah, I don't write probably not all of them down now, but they should hold. I say obvious relations hold. Okay, and when we apply this whole theory for categories, then there's the notion of product in set. So set with products. So the Cartesian product and the 1 point set. Sorry, the 1 point set is a monoidal category. And when we do this, then in the next step, we will get some notion of what is an enriched category. And one can also define enriched functors. And this is what one uses there. And now I should maybe note this down and also define enriched functors. And this is somehow like similar, but yeah, if you do this all, then you get really this notion that you can yeah, enrich then again in the end, because then one categories come with a product of categories, and this again makes it into a monoidal category, and you go on like that, and it always works. But in the end, what's really important for the thing is that you should just remember that you can compose in all possible directions, and you get essentially pictures like these where composition is really strict and nothing happens like only after homotopy or something. This is not done here. It doesn't answer the question.
So we can define by induction, and we will have no problems with the coherent conditions. Yes.
Yes.
I suppose that we should introduce some notions as say simplicial sets or so some constructions, so which can help us to describe these coherent conditions in a convenient way. No?
Yes, of course, this can be done. For example, one can consider, I don't know, maybe it's not really part of the talk now. This would be maybe, yeah, it's somewhat prerequisite, but yeah, I could talk about this 5 minutes. Maybe
I think that the answer to Misha's question is that coherence really vanishes when we consider strict nCategories, and coherence is only relevant for weak nCategories.
Yes, that is true. We have coherence conditions, and they are just saying that qualities of morphisms is there, but no conditions. No, the thing is that it's really equality of morphisms, and all things are equal, and there's nothing like we must give a choice of composition, and we must also give an isomorphism between this something like this is not necessary in this case, because it's only, it's not homotopically like when you do this with quasi-categories and so on, and from this perspective. Right here, it's just
yes, okay. But in practice, we use weak notions.
Yes, exactly.
Than, okay.
True. And this is also the point why I want to say that this definition of that this fact here is maybe not totally best for us, because what we want, maybe let's go back to the what was the plan. So nCategories are the theta n. So this specific set of categories of the specific type of categories, the subcategory of nCategories, is I just say it's a dense category, a subcategory, and actually this is not totally what is best if we want to consider also these weak compositions, because one possible approach now is just think of these presheaves on theta and up. This at least is a rather easy category in theory, because we only have specific types of categories there, and it's not too crazy. And now maybe it's possible to do something like with simplicial sets, where you have that categories go into functors of delta op to set, which is also a special case here. If you put n equals 1, then this is a special case. And this is just the ordinary nerve. And it's also fully faithful. It makes then simplicial sets as the space of the type of object where we can generalize now, for example, to quasi-categories, where we have this composition relation, which is now slightly weakened. But the problem in the end is that it here will not give the fully correct thing, because what's the point? Put this maybe here. So n categories, there are functors of n categories that are not somewhat strictifiable, or at least morphisms and so on. So morphisms in n categories. Or just write higher morphisms in n categories that are not strictifiable. Oh, no, right. Whatever. And then this means that when this is fully faithful, then it would mean that whenever we have some morphism in there, maybe a morphism between morphisms and so on in the correct way, then it should, if this is fully faithful and this makes sense, when we have some notion of a wreath category. So if some notion, if it is possible to give notion of wreath category, and now get some subcategory of these presheaves on theta, such that these are exactly the wreath categories, and their morphisms are morphisms of wreath categories, then this being fully faithful would mean that all those are strictifiable. But this is just only true for maybe case 1, but in higher cases, this is not necessarily true anymore. So it doesn't immediately work like that. Okay. Yeah. So in the end, this approach will not totally work, but nonetheless, today's talk is about this. So just bear with me, and we will take, instead of talking exactly about this point, in a bit of another direction. Namely, I want to also give at least the basic constructions of different ways to construct this theta category. So we have at least now, okay, maybe I didn't fully make the promise here, fulfill the promise that we see that this presheaves on this theta, at least if it's true what I stated, then it's not possible immediately to give the correct notion. And but still they are worthwhile to study. Therefore, we should consider different approaches to theta, and maybe this just helps in the end that one can adapt this definition and make something slightly different and obtain really a good notion of the category. Okay, but to do this, we will now define alternative ways how to view this theta n category by more adaptations to this tree perspective. So this is the next part. More alternative viewpoints of view viewpoints of theta n. Okay, the first thing which we can do is we slightly modify these trees. Oh, no, not yet. First we do disks, and this is the second part. Yeah, disks. This is the second part of the title, and it works like this. So when we have a tree, when we have a tree, something like here, I just draw a tree. Maybe like this. And then it corresponds to a disk. And what's a disk? I draw first the picture and then tell something about this. Namely, we have in dimension 0 point, call arrows, D0. Yeah. Then in the next step, there is this corresponds to here. The next we have this one, this corresponds to there. And then we have maybe this should be right still. Yeah. And these ones correspond to 2 over here. And maybe if you want to add more stuff, we could do this. Add here a subtree. And this corresponds to adding here morphisms like this. And I think it's you can see how this approximately works. We draw an n disk. We draw an n disk at the nth place, and then the 0 part is just the point, and the fiber of this the projection of the interval down to point, we always project 1 dimension away, and so here everything is contracted maybe to the middle line, if you want to think of this like that, and but then you can just project down here, and here everything is contracted in this way to the point, but it's the same as projection. So we choose orders of coordinates, and then we draw exactly the pre-image in these disks. So one other example, and this is an example of a finite disk, because what we really consider as data of the disks is only these points. So the other stuff is not there, only the points. But if we maybe just do an example of an infinite disk, this may be a bit more easy to see what happens. And namely, an infinite disk would be, let's take really as nth part, the ordinary dn, and project, so this is just the space of all the point x, such that the maybe like this, and this x lives in R to the n. And this projects down to dn minus 1 by ignoring the last coordinate and so on. Then we can go down until d0, which is a point. Okay, and this would be an example of an infinite disk. Let me draw this basic picture here, just the same as we have already seen. It's like this, here and a point. And okay, maybe just for convenience, one additional picture of the next dimension I draw smaller, because it's not too much important. I will not reference this too much, because sometimes the dimension gets too high. We work with the picture below. But yeah, okay, this looks like that. And so now, what are properties of these disks? There are various maps here, which call the projection. We will always call P. But to distinguish them, maybe this can be called P1, P2, P3. And then, of course, the middle part is contained here. And then there are also maps like inserting these points back maybe at the start here or at the end there. And we call this, if we order them like this, then this would be the bottom, and here we have the top. And the same we can do with the next part. We can embed this here, or we can embed it here. And this would be also bottom and top map of the interval. So yeah, one can give numbers, but in the end, it's not too important anymore. We just remember where we are. This is possible. I think it's too bad if I just delete them. Okay, and these are already a few morphisms between these objects, and there are of course now relations. So to give a formal definition of what's a disk over sets is the following. Disks in, let's say, sets is a model of the following logical theory. And this is the theory of disks. And over the language, so we have a language, and these are now types and relation symbols and function symbols. So what we have is the language consists of, we give us function symbols Pn, and this goes from dn to dn minus 1. Then we give us, for all n of course, then we give us bn tn, and they go from, let's let them all be in, I can't decide where they should go, but maybe a plus minus 1 arrow, but it's not too important. Go back. And then we have also a relation, is a relation, relation on relation symbol on dn. So these are the types of these are the types, and there are then function symbols and relation symbols. And now we want to give a logical model, and we now need to say what theory is, what axioms this should satisfy. So in the end, if we give a structure that in set, that would be just a set for all of these types, and an ordinary function for all of the function symbols, and then a relation for this relation symbol, such that the following axioms hold. A disk is then an assignment of these symbols functions, and first of all maybe objects. Maybe I just immediately generalize this slightly. Objects, morphisms, and sub-objects of the n cross itself. Here, namely, for what is what, here the objects, this is for the dn's, the morphisms, this is for the p, the b, and the t's, and the subobject is for when we want to say what does the relation here mean, and such that now what should hold. So we want that first of all this is a relation, is an ordering. So it's a partial order. This is the first thing. Second thing, it is a total order on the fibers of P. So in this way, one can say that Px equals Py. So X and Y are in the same fiber. If and only, this is a symbol which one uses in this case, if and only if X is less n, or I just write less now, because we just remember in which dimension these X and Y live. This holds, or Y less than X. And this says that it's a total order on the fiber. And the next one, we should have that B and T are sections. Hence, we have that it always holds for all X that P of B of X equals X, and also P of T of X. So B and T are sections. Next one, we want that B and T are the bottom and top elements, and therefore B of Px is less than or equal to X, which is in turn less than or equal to the top element in the fiber. Okay.
Sorry,
so
what is XPTX?
This means that when we have here, for example, an X, this is X, then the section sends it down to here, which is P of X, and then this would send it back to here in this case B of the projection of X, or to T of the projection of X. And if now the ordering goes upwards, then you can see that X is the line is a bit not straight, but whatever. This goes exactly in the middle, and B and T are the endpoints.
Yeah, okay. I just got confused by the notation, I guess, because you wrote like something like XPTX. Just
yeah, sorry, maybe one can add also these pictures here, but I deleted them because of better readability. Okay, yeah, these are at least a few the main okay, these are a part of these relations, but we need to have a last property, and for that I will reconsider drawing this here. So let me first remove some parts of here to show it really. So okay, what do we have when we look at where these two embeddings coincide? So when we have the interval here, and we embed it on the top and on the bottom, so when we can consider a point on here, let's run this color, X, and if it lies here, then bottom and top embedded here. But if it lies exactly at the endpoints, then this will be in both cases the same point. And how can we characterize the locus of where this happens, where this is like the singular set of this disk? This happens exactly if the points we're coming from in the bottom itself was the bottom and top element in from the previous iteration. So this okay, it was either the bottom or the top in this case. So this also happens in the next dimension. The points where the bottom and top inclusion, so in this case the inclusion on the bottom half of the sphere and on the top half of the sphere coincide. This happens exactly on this line on the horizon, and the horizon now is exactly the image of the bottom and top inclusions of this interval. So to state this is the last condition, and this is the disk condition. And it says that the two embeddings are the same. B of x is the same as top of x if and only if there is a y in the lower dimension such that x equals b of y or x equals t of y. And it's in the image of either b or t from one dimension below. Could also be in both, but yeah. So this is the disk condition. Okay, and now we have a few axioms, and the notion of a model. Maybe it is necessary to explain the theory of models. And I already said that this thing here is more or less an assignment of these things is more or less called a structure, and if it now satisfies all these axioms, it is called a model of the theory. And there's also an obvious notion of map between models, and this would just be a map and a morphism in the category sets in this case that takes each type to a type to the each realization of the dn to the dn in the other model, and such that it commutes with all the possible function symbols and relation symbols also are preserved. So this is the obvious method how you can now state what is a morphism of these disks. Okay, and it turns out that morphisms of disks or maybe it's not to set this. Okay, I just write it another way, right? It gives a disk category. We obtain a category disk. Which has exactly these morphisms as objects, and we can also consider maybe do this in an arbitrary category which has enough structure. In the last talks, in some of the last talks, there was the notion of topos was discussed, and this is a suitable place where we can do this because it is possible to interpret these stuff. For example, I talked here about subobjects. This is a notion which we have in topoi, and all the other stuff exists also. And then if we have this category of disk in the topos, and when we have now what was the point? Now theta n. Yeah, one thing to say maybe we can also restrict everything to just up until n. So if we truncate at n, then we obtain disk n, truncation of these structures at n gives the only up to n dimensional disks, this less than n in E. And what we have is that theta n is the category of now additionally finite disks. So we have disks theta n that are finite and that are in sets. So just set-based disks, and there are finitely many places, it's less than some n, And all the points that we choose there that are in the structure, that are in these intervals, are only finitely many points. And then we not do an opposite here. So it's the category opposite.
So does it mean that we just take a model in finite sets, or?
Yeah, can also be done like this. Yeah, maybe this is better way to write it. Okay, and how to see this? Let's go back to the trees and see a bit how we can relate this notion of disk to the notion of trees we had before, and also see how we can have morphisms of trees that give morphisms of categories, and why this is now contravariant. So for that, I again draw a tree. Maybe this one. And let's also draw the corresponding category. This would be 2 objects for the base case here. Then we have 3 morphisms there. Okay, and this corresponds to the 3 sectors here. And now what we will do, maybe I add even another part here because it's better to see it now. And let's add another morphism here. So we have now the objects there and here. So these trees, this tree corresponds to this category. This is a tree. This is something in theta n. And how can we draw the disk that corresponds to it? It looks like it suffices to do this for 2, so we can just take this part, and we have now 2 lines, namely this direction and this direction. Maybe I'll do these other colors. We have, let me do screen, I already use it. This and this, and there we have 3. Oh, wait, what am I doing? Yeah. So again, we have in the base case, we want to project down to just 1 point. Then we start with 2 points. So we have 2 vertical directions where things can live. And in one of them, there we have 2 pre-images. In the other, there's only 1. So it looks like this. Which goes down to the interval, and then this at this point. And yeah, maybe to give colors to make it explicit. This corresponds to these 2 objects. And wait, no, there's nothing here. Sorry, I made a mistake. No, like that. This one corresponds to this one, and this one corresponds to this one. Okay, and then the thing what we can do is we simply insert the endpoints to the picture, namely here, here, and also on the top, like the extremal parts, in all the pre-images, like this. And what this would mean is in the other picture, we could just add, maybe I draw them a bit smaller. We could just add formal edges at each part of the tree that correspond somehow to exactly these endpoints. In this sense, now, instead of talking about sectors, a sector is now a pair of consecutive edges of consecutive children. A pair of consecutive children of the node. Earlier, this didn't work because the outer sectors only had one adjacent node there, but now it's really a pair always of the node. Yeah, at a node. Okay, and now let's see what we could do with this. Maybe we want to do something like, what can we do? We can, a map of trees is just a map that preserves all the edges and incidence relations and sends these formally added vertices at the end. These are what I call the exterior vertices, and these are the interior vertices. And the exterior vertices should always map to the exterior ones in the tree notion, in the tree morphism, and the other ones can map arbitrarily. And morphisms that appear in this way are then, for example, given by, so let's do again an example when we have this thing here. So again, two formal vertices. These are formal. I draw this in the arrow here for I did a circle for the form that is exterior, and this would correspond to the morphism to the category that has 3 sectors, therefore 3 objects and 2 morphisms. Okay, and now maybe we can put this together to just I mark the pre-images. So wait, so this is the pre-image of this point. They both go to here. And if we do that, then what this corresponds to on the other side, because here we have on the bottom, it corresponds to this category because we have only 2 sectors, so 2 objects and 1 morphism between them. And what we want to, in the other side, it's now the embedding, or not the embedding, but yeah, the embedding of this category into the composition of those 2 arrows. So this is the composition, and now it's embedded here. So this is what this corresponds to. Another thing that one can do is when you have the same thing again, but now maybe we put those 2 to just the vertex here. They go to here. Then in the corresponding picture, this would correspond to inserting this category into this side. So this goes to there, and this goes to here. So why must it be exactly like this? If we draw the arrows, oh no, wait, I'm dumb. Sorry, this is the wrong direction. I rather want the other side. I come now why this is the case. And we have here 2 arrows, namely here, the first one corresponding to this, and the second one corresponding to this. And by somehow sending the blue one to the exterior vertex, we delete it in this sense. So we should think of this as being deleted because it goes outside of the interior. And then only the other part is preserved, and it will now be exactly this embedding. On the top part, we have that both of these corresponding arrows go to the same one here. And this means that the corresponding morphism it goes to the composition of all the morphisms in its pre-image. Is this more or less clear how you should compose, how you should produce from a morphism of trees? You can produce a morphism of categories, at least in the one-dimensional case. In the higher dimensional case, this would then be inductively pasted together when we do this at a subtree. Are there questions for this? Okay, then I continue a bit. So now it's maybe a bit easier to see that at least these tree morphisms, they will correspond to the category morphism. And this is, maybe one can formulate it as a theorem that this morphisms of, or maybe write it like this, category of trees is let's say a level n trees is isomorphic or equivalent, whatever, to theta n up. And tree is of course here maps are exterior edge preserving morphisms or graph morphisms. Okay. What can we do further? So maybe to go about this part on the why one could ask now the question why I formulated this theory here. So in this form, why I used this. I formulate this as a theory and not just as some less formal way, in some less formal way. And the reason why this is formulated like this is that it really allows some topos theory here, and it shines through. And what is the theorem for that? So the theorem is that presheaves on theta n is the so-called classifying topos of n disks, of the theory of n disks. And maybe it is in order here to define this again, and also to should I say this? Yeah, sure, maybe. So what's a classifying topos? We already in a bit defined what it means that a logical some structure is a model of a theory in the topos. But I only hinted at it. I did not really explain it properly. If the time is there, I think it's there. I can explain this. So I do this now. And additionally, we can then see, or at least we can state that what it means to be classifying topos. So what exactly do I mean when we have some theory and we interpret formulas in a topos? And this comes to the sub part of shortly a bit of internal logic. So we always in a topos have this sub-object classifier. which is very important for the theory. So it's and how does it work? There's an object omega and a morphism from the terminal object, which I call true. Sorry. Such that whenever we have any x, and then in the subobject of it, so A is some subobject. So this is a monomorphism. And then there is a unique map of this that makes this into a pullback diagram. So in some sense, it's a moduli space of subobjects. Yeah, and this is one part of the definition of an elementary topos. And we have also the other parts that say that it should be Cartesian closed and it should have limits, finite limits at least, and co-limits. Something like this is also necessary. But the main part, which gives all one could say this that it has these finite limits is of course important. Otherwise, it won't work. Already, this condition doesn't work. But the main part of the why it's so powerful will be this subobject classifier. And then what we want to interpret formulas is the following. We instead of considering the formula itself, we consider the subobject of all the somehow more or less elements that satisfy this formula. So when we have some phi, a formula, then it's somehow in bijection. Maybe there's some free variables. Let's write just x for this. I just assume that there's one free variable, but we can generalize it by using a product of variables or some product type. If we have now this phi of x, then this corresponds exactly to all the x in x such that phi of x holds. And this is a subobject of the domain where it lives. And in this sense, when we give a formula, we can equally well give a subobject. And so now we say that when we have some formula phi, and we have an assignment in topos. So maybe I thought I still given an assignment or an object x m in a topos E. This is a topos. And this x to the m, it just means that we have interpreted this sort or type x in the topos. And we assume that all the possible things that could appear in phi, like functions and relations, are also suitably interpreted as functions or morphisms or relation and relation symbols. And if we do this and assume that this works at least with the phi, then we can say what it means that the formula holds. So we say that what do we say? Maybe write like this: E satisfies the formula phi. Okay. Yes. I think I should write some x here. Oh wait, nonsense. Yeah, we can only say this when we have. Sorry. Should start with something before that. given an element.
Sorry, what do you mean by x m?
Yeah,
above?
I mean that just a chosen object.
This is an exponential.
No, it is not.
Object.
Maybe I wrote it on the bottom. It is just any chosen object in the topos, and then M is just the name because we maybe call this a structure or a model in a hypothetical structure M, or just say in a structure M. And this is just a name for the structure, and now we have chosen some object where we now interpret this. And now if we give us any given any morphism W to X, this interpretation of the type X, let's call it sigma, then we say that E satisfies phi at sigma if the following thing holds. We consider this W, this goes to X, this goes to omega, and it comes from here 1. This is the true morphism, and here we have this set where the formula should be true. Goes to here and here, and then if there is a lift there, of course this is a subobject, and then there should exist something, and necessarily it will then be unique, but we don't need to write it because it will be unique, because if this commutes, then this is a monomorphism, then there can only be one morphism like that, but it's not important. We can just prove that it exists with equivalent condition. So this is the condition that is called. Another thing is, how do we get these objects? This is the main point. Get these. So the idea will be that we have some notion of to get this subsets, more or less, where the formula holds, and then we can talk about that some sigma satisfies this because it lives in the subset, which is expressed by commuting in this picture, by factoring through the inclusion. And now the only thing is one needs to really get all these subobjects that really this is the main point. So to answer this question, this will be done inductively. Inductively by the structure, or via the structure of formulas. So what we do is we interpret the subobject where wrong holds, so falsity, this is just the initial object. Then the subobject where truth holds, this is the whole, the complete of X, and maybe with the inclusion here the unique one, and here the identity. And then another thing what we can do is when we have all the X such that maybe a term, let's say F, f is a term in X, and this should be equal to another term. And a term is just some composition of relations or function symbols. And this we just define as the equalizer of the maps that are given by these G and F. So equalizer of the map that X, and then there are two maps that go to some X prime, and these are F and G. And however the term works out, it is defined by some collection of basic function symbols, and all these function symbols had realizations as maps in the topos, and so we can compose them together, and then they end in whatever type this is. So this will be then an element of or this will be have type X prime, and GX similarly, and then we can talk about the equalizer there to interpret this equality. So that's how that works. And now we have the basic types of assertions that we can do, or formulas, namely falsity, truth, and equality of terms. And if you look back, these appeared here in the definitions. Here we have these terms, and we have also sometimes truth. No, we don't have truth, but if you want to think of this, maybe if we just write the symbol without something before, then we could write true before, maybe add this. Then we have used them, and yeah. Okay, and to get the other stuff, this would be then maybe if we have already interpretations of phi and psi, then we want to get an interpretation of the composition of the conjunction. And this would be then all X, such that phi of X and okay, I can somehow more or less delete this. Not too important. We just remember that X is the three variables in there, and what this will be. Here all definitions. This is exactly all X such that phi holds, and then the intersection with all X such that psi holds. And what is this intersection? Well, it is the pullback of these morphisms. It's like how do we do it? So we can consider this object. Maybe I just write this in a slightly different way. Copy this to here. Copy this to here. And then we have this just as the pullback in this diagram. That goes completing it in the corner to X. And here we have the respective inclusions. Okay, and this is then the interpretation of the intersection. Then how could we interpret the interpretation? How could we interpret the disjunction? This would be, wait, okay, now it works. Disjunction would be as here we take the image of the morphism that comes from, well, again, the same two guys. I copy it now. Image of, but we take now the disjoint union and consider the morphism of the respective inclusions to X. And when we do that, then this will be the image. And maybe on both parts, you can consider the corresponding morphism. This defines something incomplete. And then in the topos, there is an image factorization. As factorizations of all morphisms into into IP, where f equals IP, where I is mono and P is an epimorphism. So first some epi and then a mono. This is the image then, and then the image is actually uniquely determined by this property. I won't prove this now that this works, but it works if you assume these axioms that the topos should satisfy. Okay, and this is how you describe the union or how to interpret the or juncture. And maybe the only thing that is still necessary, I think, is the existential quantor. We had an existential quantor up here. If you remember this, then there was here we had an existential quantor here, and to interpret this one, it's maybe slightly more confusing, but I will do this now. I'll give the definition of that as well. So to interpret this, we have, of course, a formula phi that lives in the three variables x and y, and then we have there is y such that phi of xy holds, and this should have some interpretation. And well, to write this, they should be called then the object of all x such that this holds. And here we have the object of all xy such that this holds. And this, of course, is a subobject of x cross y. This is more or less the definition how this works. When we have more than one free variable, then this will be in the product, subobject of the product, and also for the morphisms, how the terms are interpreted. Okay, and here this should live in x. And then we have the map here. We can do the projection. We just project to x. And when we have now this bottom morphism, again, by this image definition, it is possible to factor it in such a way that this will be an epimorphism. So in essence, if we call this composition alpha, then this here is the image of alpha. Okay, and this is how to interpret the existential quantum. And when you do this in this way, then we have now, I think we have now interpreted all the possible symbols that in theory appear in these formulas. Yes, okay, this partial order, if you extract it out, then this is like the three transitivity, reflexivity, and the ordering anti-symmetry property. And this just is also expressible in only basic terms that we have already defined. And all the other things are also there now. And so in theory, we see now how it works. And we can state what happens down here. So let me go on for 10 more minutes, then I can get to an end. Now we wanted to define what's a classifying topos. For that, we went this detour on internal logic, and now we come back to this definition of a classifying topos, namely a definition classifying topos this is you write it T, a theory over some language, and then a classifying topos is a topos set adjoint T such that we have an isomorphism, a projection, such that there's a projection of models of the theory in another topos. I maybe state again how this works in a minute, which is in projection to the, let me write it as geometric morphisms from E to set T. Maybe there are words now that I should define, namely, what's a geometric morphism? So these are, by definition, functors from E to set T, F in there, that admit an adjoint, a left adjoint. And this adjoint such that F has a left adjoint, which is left exact. This means commutes with finite limits. Even though it's left adjoint, it should in theory only commute with co-limits, but it also commutes with finite limits. So this is the notion of a geometric morphism. It's maybe a bit strange why this works out, but yeah, in the end it works. And on the other side, maybe, yeah, let's see whether I have time to say a bit, one or two words about this. But on the other side, the models are simply the, as I said, we for every type of the language, we give us an object of the topos, and for all the function and relation symbols, we give us a morphism or a subobject of the product of this, of whatever happens there. And in the end, then it's a model if these interpretation of axioms in the theory using these formulas work out always for all possible sigma that there are. So to state this, gleich equals set of structures. So these assignments such that stuff happens that satisfy the axioms of the theory. Or axioms of T. Okay. And now this is somewhat interesting because what we have now didn't prove it, but at least this is now true, that this topos of disks and this theta pre-sheaves on theta n are exactly the classifying topos of the theory of disks. And a special case maybe of that, if we specify to n equals 1, specialize to n equals 1, then this means that pre-sheaves on theta n or theta 1, they are exactly simplicial sets, because this one is delta. And what is a one disk? We can look this up in the definition from the top. So a one disk is this. A one disk just has these conditions, and there's essentially only one projection and one inclusion of B and T, namely in this part here. So this is the only thing that happens when n is 1. And you can see that it's just an interval then, because everything is the fiber of the point. And at points are different. This follows from this condition here, because if n is 1, then this existence is not possible because there's nothing in degree -1. So this part is always wrong. Hence, it is never the case that B of x is equal to T of x. Hence, these end and start point are different. So we have strict intervals then. Yeah. Okay, and similar to just the statement I gave that disk is opposite to the category of theta n. This finite combinatorial disks, so these finite disks that are in sets, that they are opposite, that their opposite, its opposite is the category of theta n. But the proof is was today more or less a bit by suggestion. This is not a formal proof, of course, but in the case of delta 1 and theta 1 and simplicial sets, maybe it's a bit easier to see this, that it actually works. And I think there's a nice picture, but what you can do to see that delta is actually also isomorphic, or at least equivalent to the category of intervals but duals. So maybe finite disks, this would be how they write it, disk less than 1 in finite sets. Hop. So one could call these just intervals. Or maybe for short, if you want, I write int now. Okay, how to see this? This is like a side argument, but it's a nice picture that you can draw here, which is why I want to do this in the last minutes. And namely, consider an object in here. This would look like something like this. So you have just n stuff there, and then this would be the object 2 because it has 0, 1, 2. And here we could maybe put the object 3, which has then 4 of these. Okay. And a morphism in general looks like something like this. Sorry, what am I doing? Something like this. Okay, yeah, now it works. And now to get the dual morphism in intervals, you just insert bars like this between every combination here. And if you also insert them on the outside, then you have this being the bottom, this being the top, that they're disjoint, because we have at least one point in the middle and then at least two on the sides. So these are strict intervals and finite ones. And now the morphism is, we just consider, we just go from an interval here. There's a unique way how to draw an arrow that doesn't intersect any of the previously drawn ones. And this is what you do. And in this sense, again, this gets you order preserving maps. And this really shows that these categories are equivalent or isomorphic, depending on whether you think of this as a skeleton. But let's think of this as a skeleton, and you get an isomorphism of intervals and the opposite, the opposite simplex category, which also makes sense then, because it just says that functors from intervals to sets, which is just simply resets by the above isomorphism, that they are, this is now the classifying topos of intervals. And maybe it's not too bad to believe this, because what are these things? These are more or less sets in the shape of an interval, or with intervals. And if we would just have sets, then this would be more or less the empty theory, just nothing, apart from the obvious, like the point. And the category of sets is also just sheaves on a point, so it's like the point topos. But now we have interval shaped sets in a sense, and they classify now intervals. And the same holds true with disks in this case. The pre-sheaves on theta n classify disks. Okay, and this is the things of today's talk. Are there any questions?
Yes, I have a stupid question. Was the reason that delta is the same as theta 1?
Let's see.
Okay.
So this comes from here somewhere. If we take this definition of delta, where is it? There, linear enriched categories, and only do it once, then linear categories are what I call linear categories, is just objects are one after each other, and then there is one morphism in there in the end. Because the base case, maybe one could write it, theta 0 would be just a point. So the pictures in N are more or less by definition always in this form. Does this answer the question?
Linear means that we have a sort of direct graph.
Yeah,
or
we have the linear graph that looks like this, and then we take the free that only adds the compositions of all the possible arrows, but no relations.
Okay, thank you. And another question. What is the rule for constructing the left-hand side image by the by the tree or graph? I mean, you draw a tree, and from this data you can draw the picture like this in center of this colored picture between homomorphisms.
Exactly. If you have any, if you look at some subtree, for example, this one, this is a subtree at a vertex, and this vertex this corresponds exactly to a linear part of the morphism. So here we have one part, here we have another part. The first thing, nothing happens anymore. This is where we get this first part. And the second, this is where then this subtree is inserted. And inductively, this subtree here, this was constructed as the category that had two objects. So it looks like this. And if we insert this into here, then it's turned around and put in into there. It's turned around and inserted as the yellow arrow between two objects, more or less, because now objects are one dimension higher because we have considered this as attached to the subtree at one level higher. And in general, this is always how it's done. So the base case, we have just a tree grafted, many arrows grafted to one, and we have exactly that many morphisms. And when we look then at any higher thing that adds something here, where can I go? That adds some stuff here, then exactly what is added is added in the picture. We add this many arrows and the corresponding morphisms between them. So then we get like this tree embedded into this direction. And then we would continue in this way, depending on where the other stuff is attached there. Does it make sense?
Okay, thank you. And could you move to the bottom of your notes?
Yeah. Where's bottom?
Yeah, here. And what do you mean by okay? What does it mean, disk of some category? You mean that on each stage of your tree, you consider objects from this category, yes?
Yes, exactly. It would
okay.
Yeah.
Yeah.
But I could also write this as in the formal notation as models in finite sets of the theory of disks, but we only have the axioms that consider the 1 and 0 part. So we have only the type D1 and D0 and only the B and T in the first case. So we truncate the axioms and possible things.
Okay, and in this picture, we have a green objects and white
Yes.
objects. And so what is the relationship between them?
So this here is the morphism of in delta, and the green morphism is the corresponding morphism in intervals. Therefore, we want to prove that delta op is exactly intervals, and delta op is defined by, it has only these order preserving maps, and intervals as well. There are only order preserving maps, but also the exterior points must be preserved, because the bottom and top inclusion should be preserved in the definition of this disk stuff. This is where it comes from. But you can just now take it for granted that the bottom and top should be preserved. And now one can see via this process to draw these edges in this way that the arrows are correspond to the blue morphism and the red one correspond exactly to each other if we do it like this. So this and this correspond to each other if we use the procedure described, that we always insert the arrows such that it fits without intersecting the other ones.
Okay, and the last question from me, and how can we construct the model of weak and category by means of this construction?
Yes. So that is the thing that I a bit gloss over. Yes, true. This is important. So of course, this is all strict. This was all strict. And if we now want to give some weakness assumptions, then we could do a similar approach as it is done for quasi-categories. We could consider only maps like, we can consider faces of theta n categories, faces of theta n. This is an object in theta n. So it's to draw a small theta here. And what would it be? This maybe one could draw it as delta S theta, and S is some morphism of the corresponding trees. Morphism from theta to theta prime. That contracts exactly one interior morphism that reduces the number of interior of interior vertices by exactly one. So essentially, you compose one possible morphism in this sense. In the last dimension, there's one composition happening, and then you, from this morphism, you get a morphism of this form of in the other direction, and we call it now in this sense. Maybe to draw this, I draw this. If this is now a tree, let's call it maybe T to T prime, and then this here corresponds to this corresponds to T, and this corresponds to T prime, and then we have some face here that has some composition in the sense. And if we do that, then we can again form a horn, namely S of theta is then the union of all but one face of theta given by S, of the face given by S, of the S face of theta, but we must consider it considered in pre-sheaves on theta n, because we can't consider it as in theta n because then there's no union notion. It's too difficult. We must consider pre-sheaves, but we can embed theta via the Oneida embedding into pre-sheaves on it. So it's the representable, the standard simplex, like standard simplex, and then we can collect all the possible faces there. And now there's also a notion of interior horn. So inner face is then something that all the interior vertices are preserved in the tree notion. And we obtain that we can similarly to the quasi-category definition, a weak form, maybe one could call it a pseudo n quasi-category, is then a pre-sheaf such that all of these S theta to theta here for all maps in this form and for all S, for all inner S, this map here admits a lift. So the last part is just the same definition as for quasi-categories, and the other parts are slightly generalizations of what happens in the quasi-categorical case as well for simple sets and bonds of standard simplices. Because if you restrict this to the same situation, exactly this happens. Let's look at the picture here. We have this one here. Here, the two interior vertices are preserved by this tree map, and we get the composition inclusion. So in the picture of the simplex, the composition lives here. These are like this. But here, this interior vertex gets sent to an exterior, and then it's the inclusion, which is not the interior face. So the only thing that is now the interior horn is the theta 1, 2 in this case, sorry, theta 1, 2, that only extracts, that only excludes the first phase, which is the interior one in this case. So this is how you get this notion of recategory then. But as I said, it's not the best one, since there are these problems about the fully faithfulness of the nerve that one should only expect in one categorical case, but not in higher case anymore.
Thanks a lot.
Yeah, maybe this last part was a bit less than I expected, but of course, this is an interesting topic. One could already give another talk about this. There are many possibilities. But today I'm more or less focused on the on bit of like two definition of like trees and disks, how this gives the theta category. Okay, any more questions?
Well, I guess if there are no questions while the recording is going on, I can stop the recording.